like him? Did you see the Suicide Squad? No, but I heard that was he was the best part of it. Really? I heard the joke. I'm just joking. That's like
Okay, let's do this one. So we got to write arctangent of x over 13 as a power series, and all we know so far is things that are like a geometric series, right? A over 1 minus r. That's all we know so far. So how is this related to that form, a over 1 minus r? Right, so if we were to take the derivative, what is the derivative of this? It'd be 1 over 1 plus that thing squared, right? Is that it? Is that the derivative? Okay, chain rule, right? Chain rule, so we need times 1 over 13. And if we look at that, well, we could write that as a power series, right? That's basically 1 over 1 minus something, right? 1 over 1 minus negative x over 13 squared. And then with the 113. So we can really, we'll write this as a power series, and then all we have to do is what? Take the antiderivative of the power series we get, and we know that'll be equal to arctangent of x over 13, because the antiderivative of this will be what we want. All right, so I'll call that, I'm going to do this, grab some more room. Okay, I'm going to go fast, though. I'm going to go fast. So if you have a question, don't hesitate to stop me. So we're going to start with, say, f is 1/13 of 1 minus the opposite of x over 13 squared. And then we're ready to write that as a power series. N equals 0 to infinity. A is 1/13 times negative x over 13 squared to the n. So let's simplify that. So what is that? That is, I'm going to write it above. So that's 1/13 negative 1 to the n, and then x over 13 to the 2n. And what's that? So then we have how many 13s in the denominator? 2n plus 1. So let's do that instead. So we're going to go negative 1 to the n, 1 over 13. This really isolates the x, and then x to the So that's actually what I want to work on here. So I want to write out the terms of that, starting with 0. So when I get 0, I've got, what, 1/13. When n equals 1, I get negative 1/13 to the third, x to the squared. And then when x is 2, I'm going to get plus 1, so plus 1/13 to the fifth, x to the fourth. Let's do one more term, 1/13 to the seventh, x to the sixth. Okay, questions on those terms? So I highly recommend, for your own sake, that you kind of take this in terms of format, this approach, because as some students came in to get help from me, they kind of had things. What's that? Is it okay?
already take the integral?
No, I'm just, remember, horizontally, everything's equal. We got the fraction form, summation form, polynomial form. Everything's equal. Everything's equal horizontally, and then when we do a step of transformation, then sometimes there's more than one. Then everything gets that transformation. We're going to do the same transformation on the fraction form that we do the summation form, that we do to the polynomial form. And really, the polynomial form is just for our own being able to check that we're writing the summation form correctly. So what did we want to do to f of x to get what we wanted? We're just going to do antiderivative, and then we know this is exactly the derivative of our function. So the antiderivative is arctan of 713. So I'm going to do the antiderivative of this right here. So antiderivative will be so all this stuff will just come along. This is with respect to x, this is all constant. We'll just keep that along for the ride. And then what's the antiderivative of x to the 2n? 2n plus 1 over 2n plus 1. Okay, then antiderivative of each of these terms. 1/13 gives us 1/13 x. Antiderivative of that, 1/13 cubed times x cubed over 3 plus 1/13 to the 5th x to the 5th over 5. And I don't have room for that. Now, one thing we didn't talk about, and it never came up as an issue, but we should have, is what happens when you take the antiderivative of a function? And it's a indefinite integral. Yes. So this represents when you do antiderivative, you're really finding all possible antiderivatives, right? And so we should have added a constant, added plus c, but then we figure out what the constant is. And so I think in all cases that we saw, the constant was 0, and that's why we got away with it without doing it. But really, we should add a constant to this, add a constant to this, and then figure out what that constant is. And then we find that out by, say, setting x equal to 0 and seeing what happens. But again, in this case, arctangent of 0 is 0. Okay? So the constant ends up being 0. But so we really should have also done plus c, and then had a plus c in this polynomial, and then solved for c. Find out what c is, and you can find out what c is by plugging in x equals 0. Okay? So that should be it. And so now we just got to make sure that we want to get these terms right here. So what gives us x to the 1? Is that n equals 0? So n equals 0. Does that give us 1/13 x? I believe it does. You get positive, you get 1/13, 1 in the denominator, x to the 1. Right. Let's check one more term. So when n equals 1, we get negative, we get 1/13 cubed, we get 3 in the denominator, and x cubed when n equals 1. So that worked. So it looks like we got it. And so then I think in this particular problem, you were just actually entering in just a partial sum like this, first some 5 or 6 terms or something like that. Okay, interval of convergence. We could do ratio tests to get the radius convergence. For time's sake, we won't do it. Or do we need to do it? Do you want to do it? I see people shaking their heads. Okay, so do the ratio test to get the radius. think, if I'm looking at this correctly, would be you're going to have 2 more 1/13ths in the top than you do in the bottom, but also 2 more x's in the top. I think you get but then the rest of it's all 1. So I think this is what you have. So I think the ratio then is the radius is 13. This one?
First Greek S, and just see that for what values of x that ratio is going to be less than 1.
Yeah. That whole thing in there. Yeah, because this is exactly. So this is like your R. So essentially, you need that thing to be less than 1, and that's when x is less than the absolute value of x is less than 13. Yeah, between negative 13 and 13, you'll get something less than 1 there. Yeah. Other questions? Okay, so you'll do one more example of these in recitation, and then we'll be done with writing functions as series, but for this, in terms of the forms related to a over 1 minus r. And then we introduced last time, we introduced the idea of Taylor and Maclaurin series, so that's what we're going to do now. Last chance before I erase this. Any questions? Okay, so let's do. So remember we said that this is a very narrow class of functions, ones that are very restrictive to be either a over 1 minus r or related to that by derivative or antiderivative. That's a very narrow class of functions. So Taylor series allows us to take any function, so we start with a function f, and if you write that function f in this particular series, that will be a polynomial. So any partial sum will be a polynomial approximation for that function. If you're able to add up all infinitely many terms of the polynomial, it would be f of x in the radius of convergence, okay, within the radius of convergence. And so building a Taylor series is from scratch, from the ground up, is a matter of finding these terms, right? The value of the function at a and its derivatives. Okay, so that's what we need to do. So, and then the rest you just fill in, right? You just fill in the factorials and the denominators, and then these factors of x minus a. So you just write those down. So the real work comes in finding the derivatives, all the derivatives evaluated at a. Okay, and then we said a Maclaurin series is a specific Taylor series, and that's when you're centering at 0. And so centering is kind of like where you're basing the function, and as you add more and more terms, it'll be a better and better approximation away from the center. So at the center, usually a couple terms is good enough to approximate the function near the center, but then if you want to get a good approximation away from the center, you need lots and lots of terms. Okay, so this is then the Maclaurin series. This is the Maclaurin series. It's the Taylor series when the center is 0, or a equals 0. Okay, so we're going to do a real easy one here. Maclaurin series for y equals e to the x. Okay, so what do we need? So what we need is the derivatives. This Maclaurin is going to be, that means centered at 0. So a equals 0. And so we need the derivatives. So this is the nth term. We'll have the nth derivative. And then we need those derivatives evaluated at 0. Okay, so that when n is 0, that's just the function itself. So we're evaluating, this is just e to the x. And now we're going to evaluate the function at 0. So e to the 0 is 1. Okay, so n equals 1 means, for these terms up here, it means the first derivative. So what's the first derivative of e to the x? Evaluated at 0 is, and we quickly see that all the derivatives are e to the x, evaluated at 0 are all 1. So this column is what we're after. It's giving us these factors in the Maclaurin series. All the derivatives evaluated at 0. So that's what this table is about. It's about finding all the derivatives, evaluating them at 0, so that we can plug into the formula. So for this particular series, it doesn't matter what derivative it is. The nth derivative at 0 is always equal to 1 for e to the x. So then what does the series become? What's the Maclaurin series then? It just becomes so it just becomes x to the n over n factorial. Do you see that? Because all these terms are just 1. All these are 1, so it's x to the n over n factorial. So when you put e to the 4.2 in your calculator, someone do that. Let's make it a little smaller so it's not so big. So how about e to the 2.8? E to the 2.8. Put e to the 2.8 in your calculator. 16.45. Few more. Whoa. 4, 4. 3 fours? That's good. That's enough. So, does it have, your calculator have e to the 2.8, that value stored in its memory banks? Then how did it get this? And does it have, so how many more decimal places did it show? 4, 4, 4, 6, 4. 7, 7, 1, 1. And that's where it stopped? Okay. So, does your calculator have this value stored in its memory banks? Okay. Does it know more values of decimal places? Or does it just know enough to show you how many it can show you? How did it come up with this number? How did it come up with e to the 2.8? Yeah, this is how calculators compute values. Like, for instance, e to the 2.8. It's going to use the approximating polynomial, and what's it going to do? It's going to take enough terms until it shows you enough decimal places, until it fills up its screen. Maybe more. Maybe it will do more, but it's not going to. It doesn't know all the decimal places of e to the 2.8, because how many are there? It just keeps going on forever and ever and ever. So what it does is it uses a series. It uses a series like this and just takes enough terms until it shows a certain amount of precision, a certain amount of precision, a certain amount of decimal places. So what would it be? It's what it's doing. It's doing 1 plus 2.8 plus, right? It's just a function. So if e to the x is this, then e to the 2.8 is 1 plus 2.8 plus 2.8 squared, etc. So let's see that happening here. 1 plus 2.8, what does that equal? 3.8 plus 2.8 squared divided by 2 plus 2.8 cubed divided by 3 factorial. So what's happening? So with each term, it's going to get closer and closer to this. Was it 16.4 something? Yeah, so the more terms I add, it's just going to keep getting closer and closer to this 16.444 whatever number. So I need to the 5th, over 5 factorial, to the 6th, over 6 factorial. Uh-oh, what happened? That's just 2. Oh, it's because the numbers are getting smaller as we, yeah, so those, there we go. So now by the time I get to n equals 7, I'm at 16.3. Okay, and what's going to happen is each of these terms I'm adding, what? This is convergent series. So what are those terms doing? What are those terms doing? If you think of this as a sequence. Must be doing what? The sequence of terms. Must be approaching 0, right? If a series is going to converge, those must be approaching 0, so these are getting smaller. And they're going to keep adding on to this number, and it's going to just hone in on that number that he told me, 16.444. So when I put in e to the 2.8, this is what it's doing internally until it is satisfied that it's providing enough precision for me or for you when you read that number. So that's at least one very, very useful thing about these series is all computers, they compute values like this using series. That's how it works. So this series then converges. If we were to do the ratio test, we'd see that converges for all real numbers. Okay, it converges for all real numbers, centered at 0. And then we can use it. So now if we have something like this, so look at this right here. So say I wanted to do the Maclaurin series for x squared times e to the x. Okay, and let's think about what that would look like up here. So my original function would be x squared e to the x. At n equals 0, it would simply be 0. Okay? N equals 1. Now what do I have to do? Take the derivative of x squared e to the x. What's that? 2x times e to the x, right? No. What is it? Product rule, right? Product rule. Gives you product rule. So that will give me 2 terms, right? And so now I'm doing the second derivative. Now I've got 2 terms. Each of those would be the product rule. All right, so this is going to blow up fast, right? So these derivatives are going to blow up because I have the product rule, and it's going to give me 2 terms. Now I've got to do the product rule on 2 terms. It's going to keep. So this is, when you have a function like this, it's a product. Now finding these terms, these derivatives, is going to be work intensive. But I don't have to do that because I can just use what I know. If e to the x is this, then what's the power series expansion for x squared e to the x? Yeah, so it's going to be power series of n equals 0 to infinity of x to the, she wants n plus 2. Yeah, because I'm multiplying in x squared now into my function e to the x over n factorial. And what will those terms be now? X squared, x cubed, x to the 4th over 2 factorial. So once you build a power series, like we built the Maclaurin series for e to the x, that allows us to write a Maclaurin series for lots and lots of variations on that, just by, for instance, if it's multiplied, if it's x squared times e to the x, then I can just multiply every term by x squared, instead of building it from scratch with these tedious derivatives that would just get worse and worse as I went down the line. See that? Okay, so I want you to find a series for e to the minus 3x and find a series for e to the x minus 1 minus x. So I'm going to do e to the minus 3x. Now this one wouldn't be so bad to build from scratch, but we still don't need to because we know what e to the x is. So what's e to the minus 3x? We can just write it down. Sum of negative 3x quantity to the n over, okay, do you see it? It's just the idea of a function, right? So if e to the x is this, everywhere there's x, right? We replace x in the rule over here, the polynomial version. So now if it's e to the minus 3x, everywhere there's x, we're going to have minus 3x. So it's going to be still again 1 plus, now, minus 3x plus 9x squared question, Alec.
How did you drop the 3 with the negative 3 from the is a point in the exponent to the coefficient? Like, did that happen, or?
No, so this is the function e to the x. The function e to the x is the sum of x to the n over n factorial. So it's like a function, right? So what is e? So if e to the x is this, then what's e to the 5th? What's e to the 5th? The sum of what? 5 to the n factorial. And what is e to the y? Y to the n over n factorial. This is the idea of a function, right? So what's e to the minus 3x? Minus 3x to the n over n factorial. See it? Okay, and so then we got to think about this. Does this mean subtract 1 and minus x from every term? So does this equal x to the n factorial minus 1 minus x? Is that what we're saying? No, it's saying here's e to the x. We know the power series for that. It's not subtracting that from every term. It's subtracting that from the value of e to the x. So if we look at these terms up here, we know e to the x is 1 plus x plus etc. Then what would e to the x minus 1 minus x be? So this is not right. Instead, it should be what? It would just start with the x squared term, you see? So e to the x is this whole power series. Now we're subtracting 1 and subtracting x. That means subtract 1 and subtract x. So what does it equal? just starts at the x squared term. So we could write that, there's a couple ways we could write that. We could just write that as starting at n equals 2. We could say n equals 2 to infinity. Or we could do n equals, so we could n equals 0 to infinity, and that would be x to the what? N plus 2 over 0 needs to give us 2, and 1 needs to give us 3. And now that would be the power series for that thing, because it's the same as the power series before, but without the first two terms. And this was the e to the minus 3x to the n. Okay, any questions on these examples? So going back to x squared e to the x, I got that fired up. See how that, so the ones I've shown you before graphically converged in an interval that had a finite radius. So this one, e to the x, actually has you could do the ratio test and find out that the radius is infinity, meaning it converges for all real numbers x. As long as you have enough terms, you're going to get a really good approximation of the entire graph e to the x. Excuse me. And that's likewise for x squared e to the x. So let's see that. So here is, so the blue function is the actual function, x squared e to the x. That's the blue one. And then here is showing just the first term, so just the x squared term gives you x squared, right? So that's trying to approximate x squared e to the x. Doesn't do a very good job except right around 0, right? Right around 0. Now if I add the first two terms, so x squared plus x cubed. So notice now it's doing better a little further away from 0. Each time I add another term and look at the partial sum of this series that we got, it does a better job reproducing the function further and further away from 0. So I'll just increase n pretty fast here. So these are the partial sums. Keep adding a term each time. The radius is infinity. So meaning if all you need to do is add enough terms and you'll eventually reproduce e to the x for all x values, not just within a finite interval. So here's n equals 20. Does a good job all the way from like -6 probably to +6. I'm just not showing that. So when you do the first 20 terms, it looks good, pretty close from -6 to +6. Keep adding more terms, and it'll just keep converging further and further away from 0. But this idea of being centered at 0 is kind of like where it starts from, right? So centered at 0 means just one or two terms is going to replicate it at the center point. As you add more terms, then it converges away from the center point. Did you have a question? Okay. So that's Maclaurin's. Yeah, Alec.
Another way of rewriting this particular one, could you just make it the same equation as e to the x, but start at n equals 2?
For this one?
Yep.
No, because notice that here we have x to the fourth. So there's a shift from the exponent and the factorial when we multiplied by x squared. So now x to the fourth is over 2 factorial, and x to the fifth is over 3 factorial. So that doesn't work in this case. Makes sense? Because e to the x will have the same factorial as the power, but this now they're off by 2 when we multiply by x squared. Okay, so let's build a Taylor series from scratch that's not centered around 0. we'll do this one fast, and then we'll try the Taylor. Okay, so here's Maclaurin series for cosine of 3x. So what are we going to do? We're going to get the first several derivatives. So the function itself is cosine of 3x. Cosine of 0 is, so it's cosine of 3x, but cosine of 0 would be 1. So we need derivatives now. Derivative of cosine 3x is minus 3 sine of 3x, right? Chain rule. Derivative of cosine is minus sine. Chain rule gives a minus 3. Evaluated at 0. Evaluated at 0 gives sine of 0. Right, 0. And so then second derivative will be derivative of negative sine. Negative 9 cosine 3x. Evaluated at 0, that's 1, so now we get negative 9. Derivative of negative cosine is sine times 3, 27. Evaluated at 0 is 0. Derivative of sine is cosine. And so really what we've got now is what? 3 to the 4th. Evaluated at 0, that's 1, get 3 to the 4th. Writing it with powers and factorials will then allow you to generate a formula more easily. Derivative of cosine is negative sine, so negative 3 to the 5th sine of 3x. Evaluated at 0 gives 0. Well, let's do one more. Derivative of negative sine is negative cosine. Now we'll have 6 3's. So now we'll have negative 3 to the 6th. Okay, so here we go. So when n equals 0, we have the function evaluated at 0, which is 1, over 0 factorial times x to the 0. When n equals 1, notice what happens. Our first derivative was 0. So we don't get an x to the first term because it's going to be 0 over 1 factorial, but it's going to be, so that will go away. Next term will be minus 9 over 2 factorial times x squared plus, when n equals 3, which is 0, just write down 0, right? Because we know that that's going to be times 0. When x equals 4, it'll be plus, what, 3 to the 4th over 4 factorial x to the 4th. Plus another 0, and then minus 3 to the 6th over 6 factorial. X to the 6th. Okay, and so remember we've seen this before in like web work problems where, so our C1 term, our C1, if we were to now write this as Cn x to the n, then our C0 would be 1. Our C1 would be 0, right? Because the coefficient of the x to the first term is 0. C2 would be negative 9 halves. C3. Coefficient for the x cubed term is 0. C4. 3. And so this actually now is helping us. Start over. And C6 is. So now the question is, how can we write this with summation notation? How do we write this series with summation notation? Well, we need a new index, right? We need a new index that just gives the terms that are non-zero, right? So for instance, n equals 0 needs to give us this, but then n equals 1 needs to give us this term. And n equals 2 needs to give us this term, and n equals 3 needs to give us this term. So can you write the formula now using these new n values? So let's call them k instead, so we'll do k. So we traced it out with n's, and every other one gave us a 0 term. So now if we want to write a summation notation, we need a new index that only gives us the non-zero terms. So k equals 0, k equals 1 needs to give us this, k equals 2 needs to give us this, k equals 3 needs to give us this. So can you write cosine of 3x using k? Can you do it? So it's kind of helpful to look. So the first thing we notice is what happens with these terms. Positive, negative, positive, negative. How do we do that? Negative 1 to the k. And let's make sure it gives us the right ones. When k equals 0, we get positive, and k equals 1, we get negative. That's right, okay? So now what's kind of helpful is let's just look at these terms now. When k equals 3, we need 3 to the 6th, or 6 factorial x to the 6th. So what will it be? 3 to the 2k over 2k factorial and x to the 2k. Check it with this one. Does it work for that right there? Sure. When k is 2, we get 3 to the 4th, or 4 factorial, x to the 4th. Did you catch it? See what happened? So if we're going to write a summation notation for this with every other term being 0, we need a new index that only gives us the non-zero terms. So we set up that index, and then we come up with a formula. When k equals 3, I need that to be 6, I need that to be 6, I need that to be 6. Similarly, when that's 2, I need 4, 4, and 4. So that's the formula that will do it. Anybody have a question before I make a couple announcements about upcoming stuff? Yeah?
Why for the last two C values, C4 and C6 included the X?
Oh, I shouldn't have. Thanks. I'm just writing out the C's, right? Thank you. I just wanted the coefficients, so they shouldn't have been there. Thank you. Other question? Okay, so here's the plan. You have web work. The next web work is due next Wednesday, so we'll do a little more Taylor series on Monday, and the other web work due Wednesday on this stuff. And then I posted. Let me show you. I posted a bunch of review problems, a lot of them, and it will be worth so you can get some points. It'll be worth 2. It'll be worth. Oh no. So if you go to exam prep and homework solutions, I put up a summary of what to study, and then a bunch of problems in the book, and then a skills and concepts bullet outline. This is for your exam next Friday. So what we'll do is, so you can earn points, we'll have you